specific heat of an ideal gas. Consider an ideal gas undergoing several processes as shown in this figure, okay, whereby, right, the delta T experience, whether the path taken is from I initial to F final here, or I initial to F final prime here, I initial to F double prime here, okay, all of them experiencing the same delta T, right? Because it's from initially from the one temperature initial and finally reaching the final temperature here. Therefore, okay, the delta T experienced by each of the path taken is the same. Alright, because the delta T is the same for all of the path, right? The change in internal energy, delta E internal, also going to be the same for all of the path because the delta T is the same. The work done on the gas, okay, the negative area under the graph, as we know, the work done must be negative area under the curve. Okay, for each of the path taken, okay, is different. Okay, because the area and covered is different. Okay, therefore, from the first law of thermodynamics, what is the first law of thermodynamics? Is saying about delta E internal is equivalent to Q plus W on. This is the first law of thermodynamics. Heat, the Q, right, is equivalent to delta E internal minus W on associated with a given change in temperature does not have a unique value, right? Because even though the delta E is the same for the processes, okay, the W is not the same, therefore the Q also not the same. Therefore, our previous lesson that we have the idea of Q equivalent to MC delta T is not valid, okay, for the gas system. Special method, a way, okay, when dealing with the gas, because we know that the behavior of the gas is not the same to the liquid or solid. So we are going to have a special terms of the C for the gas, okay, where we define the C for the gas, okay, is molar specific heat. The name of it going to be molar specific heat, right? So we have two kind of molar specific heat we are going to refer to, which is CV and CP. Molar specific heat at constant volume for this one, molar specific heat at constant pressure, because we know the behavior of the gas will be different when we have a constant volume or we have the constant pressure. It's not the same, right? And the Q, okay, instead of MC delta T for solid and liquid, now for the gas is equivalent to NCV delta T, okay, for the case of constant volume, and also Q might be in terms of NCP delta T for constant pressure process. Okay, what does that mean by molar specific heat? Okay, it means that how much energy needed, okay, to raise 1 Kelvin of temperature for 1 mole of the gas. That is the meaning of molar specific heat. In comparison to this that we use to solid and liquid state of substance, it's how much energy needed in joule to raise 1 Kelvin degree or 1 degree Celsius of temperature, okay, for 1 kilogram substance. Okay, for this case, how much energy needed within joule units to raise 1 Kelvin of temperature for 1 mole of the specific gas. Now, let's take a look on this figure where we have two processes or two path taken, okay, from initial state, from the first T initial here, okay, the first process is passing through vertically to the F. Right, so here we have a vertical line on PV diagram. It means that this is isovolumetric process, or also known as isochoric. Okay, so for second process, starting from initial temperature here, okay, it's going to reach F prime here, okay, where, okay, the T final for the first and second processes are the same, right? So for this one is horizontal line on PV diagram. This is isobaric process, right? So for the first one, isochoric or isovolumetric, okay, we know that the Q going to be NCV delta T, right? So if we want to figure out area under the curve for this process, it's equivalent to 0, because if you refer to the PV diagram, there is no area under the graph. Furthermore, it can be proved that work done on the gas is defined as, but for this case, the volume is the same, one value only. So there is no delta V, therefore work done will be 0. So for the isochoric or isovolumetric, the first law of thermodynamics, delta E internal is equivalent to Q plus work done on, alright? So E internal, the Q itself is NCV delta T, because this is isochoric or isovolumetric process, plus the W on supposedly is P negative P delta V, but there is no delta V. So finally our delta E internal is equivalent to NCV delta T only. Okay, this is for isovolumetric process. All 5 processes in figure 20.3 and 20.4 have the same change in internal energy because they all take place through the same temperature difference of delta T. This statement might seem surprising because equation 20.6 contains a molar specific heat for specific process at constant volume. This one. It is true, however, due to the fact that internal energy is a state variable and its change depends only on the temperature change. So it is independent of the particular process. So the equation 20.26 gives us the change in internal energy for all processes and allow us to evaluate this change using the constant volume specific heat. So this equation can be used for all kinds of processes. And this equation also allows us to evaluate this change using constant volume specific heat. Right. In the limit, okay, if we want to have the limit of infinitesimal changes, we can use this equation to express the molar specific heat, okay, at constant volume as Cv equivalent to 1 over n number of mole dE internal over dt to the respect of t. Let us now consider the simplest case of an ideal monoatomic gas, that is a gas containing one atom per molecule, such as helium, neon, and argon, where energy is added to a monoatomic gas in a container of fixed volume. All the added energy goes into increasing the translational kinetic energy of the atom. There is no other way to store the energy in monoatomic gas. Okay, therefore, we see that the internal energy of n molecules, or n mole for this case, of an ideal gas will be E internal equivalent to K total translational equivalent to 3 over 2 n kBt. Also can be written in terms of 3 over 2 nRT. Right. For monoatomic ideal gas, E internal is a function of only T. Okay. And the functional relationship is given in equation 20.28. which is this equation. In general, the internal energy of any ideal gas is a function of T only. Okay, and the exact relationship depends on the type of the gas. Alright. Substituting the internal energy as these things, right? Into equation 20.27 gives us CV equivalent to 1 over n. This is equation 20.27. The E internal just now, 3 over 2 nRT over dt. Where we are going to have, right, 3 over 2 R for CV. Okay. This expression predicts a value of CV is equivalent to 3 over 2 R for all monoatomic gases. Right. This prediction is excellent agreement with the measured value of molar specific heat for such gases as helium, neon, argon, and xenon over a wide range of temperature according to the table 20.2 here. Right. Now suppose the gas is taken along a constant pressure, okay, path I to F prime as shown in figure 20.4 just now. Okay, I internal to F prime, right? Along this path, okay, the temperature again increased by delta T. The energy that must be transferred by heat to the gas in this process is NCP delta T because the process here is isobaric. Right. Because the volume does change from V initial here to V final here. So we do have the delta V. Right? The work done on the gas will be negative P delta V. Right? Where P is the pressure and the delta V is the change in volume. Applying the first law, delta E internal equivalent to Q plus W on, right? For this process, it will be NCP delta T plus negative P delta V. And bear in mind, equation of state, okay, for P delta V here can be used as usual because this is ideal gas case. So we may substitute P delta V equivalent to NR delta T into this equation. And as we know, okay, delta E internal is equivalent to NCV delta T can be used in all processes as Madam stated just now. Therefore, we are going to substitute delta E internal with NCV delta T, Q for isobaric, and Cp delta T, and work done on the gas within this process is negative P delta V, well, can be substituted with NR delta T. So from here, we can simplify the formula into this. Cp minus Cv is equivalent to R. R is the universal gas constant. Right. And we already know that, okay, Cv is equivalent to 3 over 2 R from equation 20.29. Given to us, Cv is equivalent to 3 over 2 R. Therefore, okay, to have Cp is equivalent to R plus Cv. So it's going to be plus 3 over 2 R. So means that this is equivalent to 5 over 2 R, the value of Cp. Right. Okay, which is can be determined from here. Okay. And if we put a ratio between Cp to Cv, okay, is known as gamma here. The ratio between Cp to Cv will be equivalent to 5 over 3, equivalent to 1.67. This ratio, the gamma here, is important for another type of process later on. In the case of solid and liquids heated at constant pressure, very little work is done during such a process because the thermal expansion is small. Okay, consequently, the Cp and the Cv for the solid and liquids are approximately the same. Okay. Example 20.2, heating a cylinder helium. A cylinder contains 3 mole of helium gas at a temperature of 300 Kelvin. A, if the gas is heated at constant volume, how much energy must be transferred by heat to the gas for its temperature to increase to 500 Kelvin. Okay, Q1 for this process is equivalent to NCV delta T. Constant volume, okay? That is how we know to use this equation. So, our N is 3 mole. Our Cv, 12.5. This is, you have to refer to table given. Delta T is 500 minus 300 Kelvin. And this one must be in Kelvin because your Cv in the unit of Kelvin. Alright. So finally, this is your Q. Part B, how much energy must be transferred by heat to the gas at constant pressure to raise the temperature to 500 K. Okay, so now the delta T, if you refer to this situation, is the same, but then another path, another method, isn't it? Another process, another type of process. It's not constant volume anymore. It's now on constant pressure. So the Q must be equivalent to NCP delta T. So substitute everything, you'll see this is your amount. So Q for second process or second path, which is constant pressure, is not the same to the Q for constant volume process. So normally we will figure out that Q for constant pressure bigger than, okay, Q for constant volume. In section 20.1, our previous section, we found that the temperature of the gas is a measure of the translational kinetic energy of the gas molecules. Okay, this kinetic energy is associated with the motion of the center of the mass of each molecule actually. It does not include the energy associated with the internal motion of the molecule. For example, vibration and rotation about the center of the mass. Okay, in this section, okay, Madam going to introduce the contribution from rotation and vibration of the molecule to the specific heats of the gas. The internal energy of a gas system includes contribution from the translational, vibrational and rotational motion of the molecules, right? So the E internal is coming from, right, all of the elements that Madam stated just now. Okay, the rotational and vibrational motion of molecules can be activated, right, by collisions and therefore are coupled to translational motion of the molecules. The branch of physics known as statistical mechanics has shown that for a large number of particles obeying the law of Newtonian mechanics, the available energy is on average shared equally by each independent degree of freedom. Okay, let's recall from section 20.1 that the equipartition theorem states that at equilibrium, each degree of freedom contributes half kBT of energy per molecule. Right, let's consider diatomic as shown in this figure, right, whose molecule have the shape of a dumbbell like this. Alright, in this model, the grey arrow, alright, in figure shows a translation in the x direction. In addition, the molecule can rotate about 3 mutual perpendicular axes as this figure. The rotation about y-axis here, okay, can be neglected because the molecule's moment of inertia, I along y, okay, and its rotational energy about this axis are negligible compared with those associated with x and z axis. If these two atoms modeled as particle, then the IY going to be 0. Moment of inertia along y-axis. Therefore, there are 5 degrees of freedoms for translation and rotation. 3 associated with the translational motion, okay, moving to the along x-axis, moving along y-axis, moving along z-axis, okay, 3 degrees of freedom. Then another 2 is associated with rotation about z-axis and y-axis. So total up, we have 5 degrees of freedom for diatomic gas. Okay, and remember, each of the degree of freedom is represented by half kBT of energy. Contribute this much of energy to the E internal of your system. Therefore, E internal for this system is equivalent to 3 n is number of molecules this is 3 degree of freedom along x, y and z axis times n times half kBt plus another 2, okay, number of molecules times with the energy amount contributed by another 2 degree of freedom, which is rotation about x-axis and z-axis. So end up we are going to have 5/2 n kBt. Okay, so 5/2 n kBt also equivalent to 5/2 nRT. Okay, so from here we can use these results to find the molar specific heat at constant volume by this method. 1/n number of mole dE/dt, okay, which is our E internal is 5/2 nRT. So settle this one, we're going to have 5/2 R. Why is it so? Because the n is cancelled out, differentiation t to the respect of t, and finally we are left with 5/2 R, which is this amount, or equivalent to, normally we remind this, CV equivalent to 5/2 R. Okay, and based on CP equivalent to CV plus R, okay, we're going to have CP is equivalent to 7/2 R, because it's 5/2 R plus 2/2 R. Right, and ratio between CP to CV going to be 7/5, okay, which equivalent to 1.40. Alright, this result agree quite well with most of the data for diatomic molecules given in table 20.2. That is rather surprising, however, because we have not yet accounted for the possible vibration of the molecule. So this one just now, rotation. We are not considering the vibration yet. Okay, if we are considering vibration, right, we have to add up another 2 degree of freedom, whereby end up we are going to have CV now equivalent to 7/2 R. This value actually is inconsistent with experimental data for molecules such as hydrogen and nitrogen as in table 20.2, and suggests a breakdown of our model based on classical physics. Okay, it might seem that our model is a failure for predicting molar specific heat for diatomic gas. We can claim some success for our model, however, if measurement of molar specific heat are made over a wide temperature range, rather than at the single temperature that give us the value as in table 20.2. So this figure shows the molar specific heat of hydrogen, okay, as a function of temperature. The remarkable features about the 3 plateau here, okay, is that they are at the values of the molar specific heat, okay, this value, okay, as predicted by equation 20.29, 20.34 and 20.35. So actually for low temperature, the diatomic hydrogen gas behave like monoatomic. Okay, that is why the prediction of this just now, okay, is not correct, right? This one, okay, correct. Okay, this one is not correct. So what happened actually, okay, as the temperature rises to room temperature, its molar specific heat rises to a value for a diatomic, consistent with the inclusion of rotation but not vibration. For high temperature, the molar specific heat is consistent with a model including all type of motion, even higher. Okay. Before addressing the reason for this mysterious behavior, let's make some brief remarks about polyatomic gases. For nonlinear molecule with more than 2 atoms, 3 axes of rotation are available. The vibrations are more complex than for diatomic molecules. Therefore, the number of degrees of freedom is even larger. The result is an even higher predicted molar specific heat, which is in qualitative agreement with experiment. The molar specific heat for the polyatomic gases in table 20.2 are higher than those for diatomic gases. The more degree of freedom available to a molecule means that the more ways there are for them to store the energy, resulting in a higher molar specific heat. So this is a table 20.2. You may refer this to your textbook. Our last subtopic, 20.4, adiabatic processes for an ideal gas. Okay, our study on molar specific heat just now allow us to complete our discussion on adiabatic processes begun in section 19.5. As noted here, an adiabatic process is one of which there is no energy is transferred by heat between a system and its surrounding. It can be done by various methods, such as the process is done very quickly so that there is no Q can be transferred in or out, okay, between the system and surrounding, or it is thermally insulated, okay, and the process is done very slow so that the Q cannot be transferred in and out as well. Okay, so the basic idea of adiabatic is the Q must be equivalent to 0. Let's recall delta E internal is equivalent to Q plus W. This is the first law of thermodynamics. So for the case of adiabatic, the Q is 0. So you have delta E internal is equivalent to W on the gas or system only. And we know that the delta E internal is NCV delta T. And work done on is negative P delta V. Alright, and bear in mind all of 3 variables, okay, for ideal gas, okay, which is pressure, volume and temperature, change during an adiabatic process, right? So if we want to have infinitesimal form of E internal and work done here, so we may put it like this, okay, infinitesimal form of E internal is NCV delta T, and this is equivalent negative P delta dV. So by taking the total differential of the equation of state where PV equivalent to nRT, right, gives us P dV plus V dP equivalent to nR dt. Okay, eliminating dt between this equation and this equation, right, we are going to have P dV plus V dP equivalent to negative R over CV P dV. Okay, now if we substitute R equivalent to Cp minus Cv, okay, and dividing, okay, by PV, we will going to have, okay, this is your R, okay, and divide everything with PV. It gives us dV over V plus dP over P equivalent to negative Cp minus Cv over Cv dV over V, which going to give you, this is 1, isn't it? 1, negative of this, so negative, negative, positive 1, negative of Cp over Cv is gamma times dV over V. Finally, we're going to have ln P plus gamma ln V equivalent to a constant. It means that PV power gamma equivalent to a constant. So, how to make use this information? PV power gamma equivalent to constant. It means P initial, V initial, power gamma must equivalent to P final, V final, power gamma. Okay. The PV diagram for an adiabatic expansion shown in figure 20.8. Okay, you may refer this to your textbook page 546. Because gamma is bigger than 1, right? So the PV curve is steeper, okay? Then it would be for an isothermal expansion, okay? We can only measure this in qualitative manner, okay? For which PV equivalent to constant. By the definition of an adiabatic process, no energy is transferred by heat into or out of the system. Hence, okay, our first law just now, we see that delta E internal is negative because work done by the gas, so its internal energy decreases, okay, where T final is bigger than T initial, alright, during an adiabatic expansion. Conversely, the temperature increases if the gas is compressed adiabatically. Applying equation 20.38, this equation, right, to the initial and final states, we see that we are going to have this equation, right? Using the ideal gas law, we can express this equation, okay, as TV power gamma minus 1 equivalent to constant. Okay, example 20.3, a diesel engine cylinder. Air at 20 degrees Celsius in the cylinder of a diesel engine is compressed from an initial pressure of 1 atm and volume of 800 centimeter cube to a volume of 60 centimeter cube. Assume air behave as an ideal gas with the gamma equivalent to 1.4 and the compression is adiabatic. Find the final pressure and temperature of the air. So we are going to use P final, V final power gamma equivalent to P initial, V initial power gamma. So we want to know P final. Substitute the rest of things. Okay, you no need to convert this unit because it's cancel out each other, and your final unit will be in ATM as well. Alright, first you get your P final, and after that you are going to figure out your T final. Okay, so since we are using actually PV equivalent to nRT, and then we are making the ratio, NR is the same. That is how we get this formula. Okay, so for this one, you have to convert your T initial in, the temperature must be in Kelvin. Right, so your final temperature will be 826 Kelvin or 553 degrees Celsius. That's all. Thank you very much. Please contact me and ask questions if you don't understand any part of this lecture.